Once more, educator Carlos Plain of Durham School states, "Absolutely, I went through my whole time on Earth enabling an unequivocal hypothesis of the universe. Likewise, at last, the hypothesis is being attempted. I welcome that, since that is the manner in which we push ahead, that is the way we make progress in science. The James Webb Space Telescope is disrupting an exceptional proportion of what has been viewed as truth in cosmology. For the new year, another ultra-deep image shows that we have serious goofs in cosmology. The telescope, which ought to show us the key stars of the universe, is changing into an enemy of the past viewpoint and may present to us a completely amazing science. Not all specialists are railing in fear at the new realities. Other well-informed experts welcome the progressions, as it has for quite some time been evident that something was off with our old hypothesis. The deviation in the evaluation of the universe's expansion speed alone ought to have shaken specialists' perceptions already. Yet, rather than resolving these issues, they conformed to old theories. The cosmic microwave background radiation, CMB, considered the oldest light known to man, was created around 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to form stable hydrogen molecules. Analysts call this process reionization, which made the universe transparent to light. The CMB was first seen in 1964 by American physicists Arno Penzias and Robert Wilson while they were working on a new type of radio-receiving antenna. This discovery was for a long time considered one of the strongest pieces of evidence for the Big Bang theory, earning Penzias and Wilson a Nobel Prize and a lasting place in the history of astronomy. The CMB probably offers a glimpse into the early universe, with small temperature differences providing crucial information about conditions shortly after the Big Bang. Scholars used the CMB as a powerful starting point for key estimates of the material universe, including the measurement of its expansion rate. The cosmologist Edwin Hubble had already established in the late 1920s that distant galaxies are receding from us at speeds proportional to their distance. Today, this observation is known as the Hubble law or Hubble constant. Hubble didn't have the advanced measuring techniques available decades later when the CMB was discovered, leading to a recalculated expansion rate. These new calculations were generally lower than Hubble's original estimate. Later, specialists recalculated the rate using Type Ia supernovae as standard candles, which emit stable light that could be used as reliable measuring points. The CMB yielded an expansion speed of around 67 km per second per megaparsec, while estimates using distant supernovae yielded about 74 km per second per megaparsec. What does this error in the universe's expansion rate truly tell us? Did you know that this anomaly has been known since the 1990s? Since that time, specialists have thought that something might be off with the assessment of the CMB, the evaluation methods, or the very nature of the universe's expansion. The difference between the observed and expected values of the expansion rate is referred to in science as the Hubble tension. The implications of this tension are enormous, indicating that critical aspects of how we understand the universe may be incomplete. For years, specialists were puzzled. Since the James Webb Space Telescope went into operation, it has provided specialists with stunning data that may now shed light on the issue of the universe's expansion speed. It has observed systems so old and mature that their development theoretically should have started before the Big Bang. These discoveries are shaking the foundations of old cosmology. Researchers no longer talk about mistakes or discrepancies in measurement. They talk about a crisis in modern astronomy. Not only could the expansion rate be incorrect, but the entire concept of expansion, or even the Big Bang itself, is being questioned. Images from the telescope provide evidence of a universe vastly different from what we have long believed. The Hubble tension was the first warning to specialists who still trust old theories. Now, they face a dilemma. Do we truly understand the universe? Many researchers are wrestling with this crisis. They examine space with a mixture of wonder and fear, grappling with what they find. In light of the crisis in science, we must ask ourselves, what do we actually know about the universe? To answer this, we need to understand how science works. Theoretical specialists use a complex arrangement of mathematical models, precise data, and logical reasoning to draw conclusions from the general to the specific. Their understanding comes from a combination of observational attributes, of measurable phenomena and theoretical interpretations. The term theory itself indicates that these are constructs and ideas, not absolute truths. The most reliable data we have come from telescope images, sound waves, and radiation collected with radio telescopes, as well as the latest findings from neutrino detectors or gravitational wave observatories. With the James Webb Space Telescope, we now have an instrument that can split light into individual frequencies and analyze it in extraordinary ways. Webb can show us the composition of galaxies in the early universe billions of years ago, their mass, the number of stars present, and the direction of their development. However, Webb has its limitations. For instance, it can't always fully distinguish galaxies from black holes with massive gravitational forces that emit light as brightly as galaxies. We must face the reality that our science has long accepted too many probabilities as facts while dismissing alternative explanations. For years, research has been overly confident in its accuracy. The latest discoveries from the James Webb Space Telescope are crucial hints prompting us to replace old theories with new insights, as has often happened in science. Analysts eagerly anticipate new discoveries that are both astonishing and groundbreaking. Many researchers are striving to develop new explanations. These discoveries shake the foundations of current science, unsettling many specialists. The current models of modern science are still largely based on Isaac Newton's laws from the 17th century. His laws of motion and universal gravitation provided the framework for understanding the physical universe for centuries. However, as science has advanced, new discoveries, such as Einstein's theory of relativity and quantum mechanics, have challenged and expanded Newtonian principles. Now, the James Webb Space Telescope is adding yet another layer of complexity to our understanding. The data it provides suggests that we may need to reconsider not only the details of our models but also the very foundations on which they are built. For example, the concept of a single Big Bang event as the definitive beginning of the universe is being questioned. Could there have been multiple bangs, or might the universe operate within a cyclical model where expansion and contraction alternate in an eternal rhythm? These ideas were once relegated to speculative theories, but the evidence now compels scientists to seriously consider them. In addition, the roles of dark matter and dark energy, concepts introduced to explain observations that couldn't be accounted for by visible matter and energy, are being reconsidered. Some experts argue that these constructs might be placeholders for phenomena we have yet to understand. The crisis in modern cosmology isn't just a challenge, it is an opportunity. It pushes scientists to think beyond established norms, to explore new models that might better fit the data. History has shown that such periods of upheaval often lead to remarkable advancements in our understanding of the universe. For instance, the discovery of the cosmic microwave background radiation significantly shifted our perspective on the universe's origins. Similarly, the discoveries provided by the James Webb Space Telescope might pave the way for a new era in cosmology, one that reconciles past inconsistencies and offers a more cohesive narrative of the universe's evolution. In the meantime, debates within the scientific community are likely to intensify. Questions about the universe's age, its rate of expansion, and the nature of its earliest structures are at the forefront of ongoing research. While some experts remain steadfast in supporting traditional models, others embrace the uncertainty, seeing it as an opportunity to uncover deeper truths. In the words of educator Carlos Plain, "That is the way we push ahead. That is the way we make progress in science. It is through questioning, challenging, and sometimes overturning what we thought we knew that progress is made." The James Webb Space Telescope reminds us of the vastness of what we have yet to discover and the necessity of remaining open to new possibilities, no matter how disruptive they may seem. As we venture further into this uncharted territory, one thing is certain: the universe still holds countless secrets, and our quest to understand it has only just begun. Motion and gravity have been the foundation of our understanding of reality and the universe for a very long time. Newton's principles explained the movement of objects under normal conditions and worked exceptionally well on Earth. However, in space, his theories required advancements, which were largely provided by Albert Einstein during the 20th century. Einstein's special theory of relativity, published in 1905, revolutionized how we interpret reality by demonstrating that time and space are relative and depend on the observer's motion. His general theory of relativity, published in 1915, expanded this idea with mathematical descriptions of gravitational effects based on the curvature of spacetime caused by massive objects like stars or galaxies. Einstein's principles and insights were critical in many areas, yet he also recognized their limitations. He knew his theory would never fully describe the universe and even referred to his inclusion of the cosmological constant as his greatest blunder, though it was later reintroduced to explain dark energy. Despite these advances, quantum mechanics emerged, challenging our understanding of reality on the smallest scales. The incompatibility between general relativity and quantum mechanics has driven decades of research, as the two theories describe different realms of the universe. Reconciling them into a unified theory of quantum gravity remains one of the greatest challenges in physics. The discoveries from the James Webb Space Telescope have only deepened this mystery. Its observations suggest that our models of the universe's structure, formation, and expansion may need a fundamental overhaul. While Einstein's equations have passed countless tests, the new findings hint at deeper principles that could reshape our understanding of gravity, time, and space itself. Moreover, questions about dark matter and dark energy persist. Dark matter, which doesn't emit, absorb, or reflect light, appears to form the scaffolding of a universe, holding galaxies together through its gravitational pull. Meanwhile, dark energy, a mysterious force driving the universe's accelerated expansion, accounts for about 68% of the universe's total energy content. Could dark matter and dark energy be misunderstood concepts, symptoms of an incomplete theory of gravity, or signs of entirely new physics? Some researchers propose modifications to general relativity, while others speculate about unknown particles or even alternate dimensions.